Welcome to the session Indexes in Oracle Fundamentals 3 using B-tree indexes. In this session, I'll explain when B-tree indexes should be used. This is the part 3 of Indexes in Oracle video tutorial series, and in this part I'll cover when B-tree indexes should be used. We'll try to understand some of the situations when the optimizer will use B-tree index, and the optimizer will use B-tree index depend on various factors, and I'll explain some of the most important factors like index clustering factors, influence of optimizer mode, and optimizer index cost etc. etc. So I'll discuss all of these topics and I'll try to explain using some examples. So although it can differ from situation to situation, that when the optimizer will decide whether to use the index or not based on certain facts like table size, available statistics, index clustering factor, several database parameters like optimizer mode, optimizer index cost etc., optimizer index caching etc., and other things. But mainly B-tree indexes are used when you are fetching very small fraction of rows from the table using the index, and B-tree indexes should be created on the columns that are frequently used in predicate conditions or join conditions of your query. And B-tree indexes are pretty useful also in situations like you are fetching many or all rows from the table and the index can be used instead of the table. That means you are selecting the columns that you have indexed. You are only selecting the columns that you have indexed. For example, you have created the table employees and you have created an index on employee ID, first name, last name, these three columns. Now you are doing select for employee ID, first name, last name from employees. Then Oracle might think that it can return the data from index itself. It doesn't need to go to the table to give you the data. So this is the example of the second situation. Okay, for example, cases like index fast full scan. Okay, so when we access the table using index, Oracle will scan the index, and from the index leaf node it will get the row ID. Then using the row ID it will read the data block from the table segment. This method is typically known as table access by index row ID. In a execution plan you can see it, and this is very efficient method when you are accessing a small percentage of rows from the table, but however it is not that efficient when you are reading a larger amount of rows from the table. And now the statement small percentage is very much relative, because in a thin table it might be 2-3% or 5%, but in a fat table it might go up to a 20 to 25%, or this percentage amounts can differ on based on index clustering factor also. Okay, I'll explain all of those stuffs, but before explaining index clustering factor I'll try to explain the thing that I have just said, like in a thin table this percentage can be 2 to 3% or 5%, but in a fat table this percentage can be 20 to 25%, based on which the optimizer will decide it will use the index or not. So what happens in case of table access by index row ID? An index is sorted by the order of index key. It might be ascending order, or in case of descending B-tree index it might be descending order. So index will be accessed in sorted order by key. It is kind of sequential access, and from the leaf blocks it will get the row ID to access the data blocks of the table segment, and data blocks are stored randomly scattered throughout in the heap. So therefore Oracle does when does a table access by index row ID, it will not access the table in any sorted order. It will not go to like block 1, then block 2, then block 3. It will not happen like this. It will search for the blocks that are scattered throughout the heap. For example, it might go to block 10, then block 533, then block 777, then again block 10. It will do n number of table access by index row ID to get each and every row, and to do it, it will have to read and reread the blocks multiple times. For example, like this diagram, this is conceptual presentation. Like this is the index leaf block. You have 100 and you have the index key 100, 101, 102 like that, and there is row IDs pointing to the particular rows in the table segment in the data block. Suppose 100 is pointing to block 10, 101 pointing to block 10 also, but 102 is pointing to block 532, 103 pointing to block 11, then 104 is pointing to block 533. then 105 is pointing to block 11, then 106 pointing to block 10. So to access the table data by index row id, it will have to read the same blocks multiple times. So there will be lots of scattered single block read from here and there in the segment. Typically in the thin table, a single block will hold more number of rows, while in a fat table it will hold less number of rows. That's the simple thing. Fat table means a table with very big number of columns, many columns, like 100 columns, many columns, and or columns with holding very large values. Suppose db block size, think about a simple scenario. This is a rough measure, just that will give you idea about this concept. Suppose db block size is 8k, a thin table have 1 million rows, and if rows are about 80 bytes in size, so logically there will be around 100 rows per block. That means the table has approximately 100 into 100, 10,000 blocks. So if you read 200,000, that means 2 lakh rows via the index, there will be 200,000 or 2 lakh table access by index row id operations. Oracle will read the blocks 2 lakh times to execute this query, but there are only 10,000 blocks in the entire table. So if the index column data that you are fetching is scattered in all the 10,000 blocks, then it will read and reread the one single block in the table on average 20 times. So in this case, the optimizer will prefer FTS rather than using the index. This is the case of a thin table. Now think about, you have created a fat table with 1 million rows, and average size of rows is about 1600k, 20 times more than the first situation. Then per block there will be about 5 rows, so there will be around 200,000 blocks. So if you are accessing 200,000 blocks by via 200,000 table access by index row id, in average you will read the block once, so there will be no rereading blocks, or there will be very less number of rereading blocks. So optimizer might think about using the index. So this is just a rough measure, but this is actually how it works, although index clustering factor have a great impact on this. So I'll just show you an example. Now for the concept that I have just explained, as proof of concept, I have created two tables. One fat table, fatty.mp, it will have around more than 100 columns, and another table, thin.mp. I have populated this fatty.mp table, and I have created this thin.mp table based on this 7-8 columns from the fatty.mp table. Both will have around 1 million records, and I have created primary keys on these tables, and by default the indexes are created, and I have gathered the statistics for these two tables. Now if I execute this query from dba tables, you can see number of blocks for thin.mp table around 9,000, number of rows same 1 million, and rows per block 108 on average. And in case of fatty.mp, number of blocks around 2 lakh, number of rows is same, and rows per block around 5. This is just a rough measure, okay, to show you the example. Now I will select 2% from the table, around 2%. Select star from thin.mp and fatty.mp where employee ID less than 20,000. This is typically 2%. So here you can see in both cases index range scan and table access by index row id, index is being used for 2%. Now let's check what happens if we access 5% of the record from both tables. Here you can see it is not using, for the thin.mp table, it is not using the index anymore, it is doing table access full. But in case of fat table, it is using the index range scan and then table access by index row id. So from here you can understand the concept. So let's fetch about 20% rows from fatty.mp tables. Let's see what happens. So here you can see I was fetching 20% records around, and it is still using the index for the fat table, but for the thin table it was not even using the index when I was fetching 5% of rows. From this example you can understand the concept that I have just explained earlier. So this percentage also can differ based on index clustering factor. Index clustering factor have a huge impact on which optimizer will decide whether when you are selecting 5% rows from the table whether it will use the index or not. Index clustering factor have a huge impact on this. So what is index clustering factor? The clustering factor is a measure that indicates how many adjacent index keys do not refer to the same data block in the table. It compares the order of the index with the degree of disorder in the table. It is typically the number of block changes while you are reading the table using the index. What this typically means, if you conceptually think, this is a index block, leaf block, and there are 4 data blocks. Okay, each block containing suppose 5 rows. Okay, suppose the scan begins from here 100, the index key value is 100 and row id is there. This row id is pointing to block 1 row number 2. So if you put a counter here, the journey begins from here 1. Now for 101 it is going to block 2 and there is a block change, it is reading from a different block, so here I put a counter as 2. Now for employee ID 102 it is again referring to block 1, so there is again a block change. I was reading from block 2 previously for 101, for 102 it is block 1, so there is a block change, so let's put a counter value as 3. So for 103 the next value again it is reading from different block 2, so here put counter as 4. Now for 104 it is reading from the same block 2, so counter will remain as 4, there is no block change. Now for 105 it is again referring to a different block 1. Okay, so the counter again changes to 5, so this is the kind of block change counter you can say. And if you go to 106, now it is pointing to block 3, the first row of block 3, so the again block change counter changed to 6. Now 107 it is pointing to block 3, again the clustering factor or the counter here it will be 6 again, cause it is there is no block change, it will remain 6. Then for 108 it is pointing to block 3 again, so counter will remain the same. Then for 109 again it will go to block 1, it is mapping to block 1. Then there is again block change 7, the counter becomes 7. Then for 110 it is reading from the same block as the last one, block 1, so the counter will remain as 7. So this is how you can explain index clustering factor. And now for this whole number of rows, index index key values, the clustering, the counter goes to up to 10 here. This is the maximum number, so here 10 will be the clustering factor. So this is kind of measure that indicates how many adjacent index keys are not referring to the same data block in the table. Okay, so if the index clustering factor is high, then Oracle database performs relatively high number of IO during index range scan, and the index entries points to random table blocks, so that database may have to read and reread the same blocks over and over again to retrieve the data pointed by the index. Okay, and if the index clustering factor is low, then the Oracle database performs relatively low number of IO during a large index scan. So low, that means there will be the order will remain same. Okay, between the index keys, the order of adjacent index keys will be similar in case of in the data block. Okay, like here you can see in these values, like 115 it is referring to block 4, 116 referring to block 4, 117 referring to block 4. So all of these values from 115 to 119 referring to same block. So this kind of like this kind of thing will because of this the clustering factor will not grow this kind of areas for adjacent index keys referring to same blocks. Okay, more of these things will be there, the clustering factor will be lower. Okay, and the smallest possible number of clustering factor will be same as the number of table blocks, and the largest possible number will be same as the number of rows in the table. Okay, and if the data is in the table is randomly scattered, the clustering factor will be high and tend to come out to the close to the number of rows in the table. If the order of data in the table matches as the order of the index key, then the index clustering factor will be low. So now let's do a POC. I'll create two tables. One table will have organized data in particular order of the primary key, and let's do it. Create table organized. I have created the table and populated the table. It will have around 1 lakh records, and I have populated using this particular PLSQL block. Now I'll add a primary key, and it will by default create a index. And in case of sequence populated values or this kind of values populated by PLSQL block using this for loop, and in case of this, thus values will be in a particular sequence in the table, and the particular index will hold the index keys in the same sequence. Typically clustering factor will be low. I'll show you, and I'll now create a table disorganized. In this statement I am using order by column 2. So the value in the disorganized table will not be stored in order of call 1. Okay, it will be stored in order of call 2. It will be disorganized, and I will create the primary key on the call 1. I am just selecting these 3 columns from organized table. Now I will add primary key on call 1. Tables altered. Now I will gather the statistics. Statistics gathered. Now from the all indexes table and all tables, I will join this, and I will show you the output. Sorry, my auto trace was turned on. I have turned it off now. It was turned on previously. Okay, now this is the index name, this is the table name, and from all indexes view you can see the clustering factor. Okay, and if you see in the organized table, clustering factor is very low. This is close to the number of blocks. This is very good indicator. And in the disorganized table, as the data is not ordered by the particular key value, clustering factor is very high, 99,700, and number of rows are 1,100,000. So it is almost close to the number of rows, and this is very high clustering factor if you categorize. Okay, so let's do it. Now I will select this from disorganized and organized, where call 1 less than 100. Now for both cases I am fetching 0.1% of record, and both cases it is using the index to access the table. Okay, now I'll fetch 1%, like call 1 less than 1000. Like if you see from the disorganized table, I am accessing just about 1% of the records, but it is not using the index anymore. It is doing table access full. Okay, from here you can understand how crucial is the clustering factor. In case of table 2, it is using the index. This is the organized table. So for example, if I fetch 10,000 less than 10,000 records, and it is about 10% from the organized table, it is still using index. But in case of disorganized table, when I was selecting 1%, then also it was not using the index because the clustering factor was too high. Now I was fetching 15%. Now even it was using the index. It is using the index in case of organized table because the clustering factor is very much low here. So from this example you can understand how crucial is clustering factor. So apart from clustering factor, there are other various things that have crucial effect on optimizer will use the index or not. Among them, most crucial is optimizer mode parameter and in optimizer indexed cost ADJ. I'll discuss about these two. This optimizer mode have several different values like all rows, first rows n, choose, rule. I'll talk about all rows and first rows n, cause these are crucially related to cost based optimizer. All rows is the default mode. If the value for optimizer mode parameter is set to all rows, then the optimizer will attempt to find an execution plan that completes the statements, typically meaning it will try to return all rows in the shortest possible time. The all rows mode is designed to minimize the computing resource and provide the best throughput. The default value for optimizer mode in Oracle 11g is set to all rows. Okay. If it is set to all rows, then CBO will favor full table scan compared to index scan, as index scan causes additional IO. Okay, I'll show you. First rows. If the optimizer mode parameter is set to first rows, then the optimizer will attempt to find an execution plan to return the first row of the result set as fast as possible. This mode is always preferring index scan over FTS, even if FTS is a better option. It blindly relies on the index scan. It is deprecated in Oracle 9. It has a problem like it blindly uses the index. Okay, while there will be many scenarios FTS will be much better. Okay, and first rows n. It was introduced in Oracle 9. The number n can be 1, 10, 100 or 1000, or using first rows in the n hint, the number of n can be any positive number. And first rows in mode instructs the optimizer to choose a query execution plan that minimize the response time to produce the first n number of rows of query result, and it also prefers index scan to access the table row. It is useful in cases like interactive front-end application or web app where you want to view first n number of rows as soon as possible. You don't care about the whole result set, but at a single time you want to view first 10 rows, first 100 rows, like that. So let's see. In this case, even if you are in case of fast rows, even if you are using a large percentage of if you are fetching large percentage of data, 80%, then maybe it will use the index. Same goes for fast rows also. It depends on fast rows n also. It also prefers. So let's do a POC. My default optimizer mode is all rows. I have created a table t_emp which have around 2 lakh rows, 200,000, and I have created a primary key on employee ID, and by default index is created, and I have gathered the statistics. So now I will fetch around 50% of the data. Sorry, I need to turn on my auto trace. I'll re-execute the query. So it is doing table access full as expected. Now I'll set it to first rows, and when I execute this, it is now using index 2 access the first row of the result set as fast as possible. This mode is always preferring index scan. It 50% of the rows, even it is using the index. So from here you can understand, like what I was saying, the in first rows mode, the index is preferred. Now even if I fetch 1,90,000 records less than 1,90,000, that means more than 90%, still it is using index range scan, no matter there are more IOs. But first rows mode, if there is a index, first rows mode tries to use the index. There are more consistent gates, you can see, than the all rows mode. It is 10,000, here it is 15,000 in the first case of when you are fetching 50% of the data. Okay, so this was one problem with the all rows mode. It blindly uses the index even if the FTS is a better way to do. And now I'll set it to first rows 100. That means the Oracle will try to return first 100 rows as fast as possible. So what happens, I'm executing the same query. I'm trying to access 50% of the data and using first rows 100 as optimizer mode. And here if you see the execution plan, it is still using the index range scan to give you the data, and it uses the index to give you the first 100 rows as fast as possible. If you see in the execution plan here, this is written as 100, and all this info here are for the first 100 records. The cost associated, the bytes, time, all are given for this first 100 records. So from this you can understand, like even if you are facing a large percentage of rows, if your optimizer mode is fast rows or fast rows n, then Oracle might use the index. So again I'll set back it to all rows, my default mode. Then I will show another thing, optimizer index cost ATJ. So let's discuss about that. Using this optimizer index cost ATJ, it is a database parameter, initialization parameter. Using this particular parameter you can change the cost of table accesses through index scan. Valid values go from 1 to 10,000 and the default value is 100, and values greater than 100 makes index scan more expensive and favors full table scans, and values less than 100 makes index scan less expensive and makes index scan more favorable. So how it works, I'm not going to the detail level, I'm just trying to show you what happens if you change the values. By default it is 100. Sorry, so here you can see it is 100. Now I'll just turn on my auto trace. Fine. So I will now set my optimizer index cost ATJ to a lower value, 20. And I will try to access 30% of the data. Then what happens? It is using the index. Okay, I have altered it to 20. By setting it to 100, let's see what happens. The default value, by setting it to 100, it is using full table scan, as I am fetching around 30% of the data. But when I have set it to 20, a lower value, it was using the index. Okay, I was fetching the same set of data, around 30% of the table. So here you can understand. Now I'll again set my this value is set to 100 now, last time I have set to 100. Now I'll fetch select star from hr.temp where employee ID less than 15,000. This is around 7.5% of data, and it is using the index as expected. As I was expecting, it will be using index. I was just fetching 7.5% of the data by default value of index optimizer cost index ADJ of 100. Now I'll set it to 400. Now what happens? According to the theory, it will prefer, by setting it to higher value than 100, it will prefer full table scan more. So here you can see it is doing table access full. It is not using the index anymore. So this is how different values of different parameters like optimizer, mode optimizer, cost index, ADJ, this can influence the optimizer to use the index or not. Based on these values it can manipulate. So this is what I wanted to discuss on this particular session. Thanks for viewing it.